how they work, because I know we all super duper need that. So the first thing we're going to do is draw a right triangle. A right triangle is special because it has one right angle. On that right triangle, there are three sides. The two shorter ones, A and B, are the legs of my triangle. The longer one is the hypotenuse, which we call side C. The hypotenuse is always directly across from the right angle. When you think about right triangles, what theorem comes to mind?
Pythagorean.
Say it, finish it.
Pythagorean theorem.
Pythagorean theorem. And the Pythagorean theorem says if I square the shorter legs and add them together, their sum will be equal to the square of the longer leg, which is our hypotenuse. So a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse.
Is that all we're doing?
No.
Just finding the sides.
But this is a baseline review, people. So, to get us even more familiar with right triangles, we're actually going to solve a right triangle based problem. So this is a nice little story problem. It's got a nice pretty picture that goes with it. So make sure you draw it. I know. Oh, no.
What did you do?
Okay.
I fixed it. It's fine.
Broken.
Okay, so here's our nice little fun little problem.
Now, I haven't wrote notes since last year. It's been a while.
Hey, dad jokes. Shut up, Jerry.
Steven, you should be writing, not talking. Devin?
I am writing. I apologize.
Oh, 20. Flashbacks. Yo, I swear, English classes at the end of the day. Math class keeps going. English class,
Okay, so the path you would be running is this yellow one, where you run down one length and one width, and then you cut diagonally across the field.
I mean, that's better than snakes.
So this story problem says, suppose that we have a football field that measures 300 feet by 160 feet. After school, you did something terrible. So your coach says that you have to run 5 miles along this yellow path. The question we are asking is how many laps along that path would you have to run to reach your goal of 5 miles? So let's let everybody write it and draw the picture, and then we will kind of talk our way through this.
Let's go to school with 3 O's.
School.
Not cool.
Is that cool?
That's what Zach said in the virtual. It's not cool to be in school.
Yeah. School was, being at home was way better.
On that note, Zach's gonna start us off.
Oh, shucks.
Okay, so let's say that this is you, and and you have to run these 5 miles. Okay, you're getting back in shape. Come on. What would you first have to calculate or identify in order to figure out how many laps it would take to reach 5 miles? I'm talking to Zach.
Your legs,
Okay, what are my legs here, Zach?
160 and 300.
So this one's 160 and this one's 300.
No, that one's 160 and the long one's 300.
Does it technically matter?
Well, no, I guess.
No, but we do want it to be realistic. So yes, I do agree that this side is 300 and this side is 160. Why do I need to know that?
So you can find the.
So we can find that diagonal distance. Because eventually I'm gonna have to know how far I'm running for each of these laps to figure out how many laps it will take to reach 5 miles. In order to do that, I have to know each of these lengths that I'm running. So we're gonna take these leg lengths and do what with them to calculate that diagonal? Use the Pythagorean theorem. So we're gonna go ahead and set it up by saying that 160 squared plus 300 squared is going to equal, we're gonna call that C squared. And we're gonna need our calculator.
Unless you could do 300 squared in your head.
So I would like 160 squared plus 300 squared. When you have an answer, raise your hand. Boone, what'd you get?
115,600.
Correct. So we get 115,600 equals C squared. So you're telling me that this diagonal is 115,600 feet long.
No, you have to square root it.
Okay, we have to square root it. Perfect. What is the square root of 115,600? 340?
340.
Wait, did you come up with this problem on your own?
Maybe,
Feet or
maybe not.
It's 5,000.
Okay.
200.
So, one thing at a time. We acknowledged or calculated that this diagonal is 340 feet. What am I going to do with that piece of information, Jeremiah?
You're going to add it, all 3 of them, so you know how far you're
Well, we need to find out.
So we figure out how far one lap is, or how many feet one lap is. So one lap equals 160 plus 300 plus 340, which adds up to what? Good for me. I figured out that one lap is 800 feet.
How many feet are in a mile?
How many feet are in a mile?
5,280.
Okay.
I figured that.
So if 1 mile is 5,280 feet, how many miles am I running?
Oh, I got you.
So I'm gonna do 5,280 times 5
26,000.
to get a total of 26,400 feet. And I'm gonna take that 26,400 feet and do what with it?
Divided by
Divided by 800.
Divide it by 800 to get the number of laps I have to run.
33 laps.
That's
Better start running. So using right triangular properties and theorems, we were able to solve this problem and figure out it would take 33 laps to reach a distance of 5 miles along this path. Any questions, concerns, or issues with any of that? Obviously, this is not realistic. Sorry, Maddie, go ahead.
How did you go from the 800 to get you multiplied 5 times the 5,000 to get
Well-
the
How did I go there? Like, how did I get that?
There's 5,000.
Because we recognize how many feet are in 1 mile. We just multiplied that number by 5 to get the 26,400. And then we did the 26,400 divided by the 800 feet in 1 lap to get the number of laps it would take to reach that distance. So the number of feet in 5 miles divided by the number of feet in 1 lap tells me the number of laps that I need. Does that make sense? Everybody okay with that? Speak now or forever hold your peace.
We'll figure it out later.
Okay. So now that we have practiced some right triangles, let's talk about some special right triangle. I love that. They're so much fun.
Are these ones easier than the other ones?
Oh, nothing we've done.
What's so special about it?
Oh, what is so special about these? That is a wonderful question, Zach. So what makes a triangle a special right triangle is that it has a special collection of angle sizes. So the first special right triangle we're going to look at is the 45, 45, 90 triangle. This is a triangle
Nice also.
that, of course, has that 90-degree angle, but the two other angles are each 45 degrees, which means that the two legs are the same length, which makes it an isosceles triangle. What is special about this is that there is a very specific relationship between the length of those legs and the length of the hypotenuse. So assuming that my hypotenuse is C, because you know that changes once in a while, each of my legs is 1 over the square root of 2 times whatever that hypotenuse length is. So if my hypotenuse was 5, then this leg would be 5 times 1 divided by the square root of 2. And I would just put that in my calculator to figure it out. Okay, so whatever my hypotenuse is, my leg is always 1 divided by the square root of 2 of that. This is not the honors class, so I'm not going to make you prove it like I like to do. But it's a hefty one, for sure. So, that was 1. I said we had 2. Anybody know the other special right triangle? 30, 60, 90.
I remember one thing from last year.
So our 30, 60, 90 degree triangle, of course, has a 90-degree angle directly across from my hypotenuse. It also has 2 other smaller angles. The smallest one is 30 degrees, and it is directly across from the smallest leg. Our other angle is 60 degrees, and it is across from the larger leg. These sides also have a special relationship in regards to their hypotenuse length C. The smallest leg, so the one across from our 30-degree angle, is 1/2 whatever my hypotenuse C is. My longer leg is the square root of 3 over 2 times whatever my hypotenuse C is. These are not something I would make you memorize, but they are something that you should have down when we do cheat sheets in the future. And remember, C is always the length of my hypotenuse.
Now, are you able to do these ones regularly, or is this just another way to do these ones?
Like Pythagorean theorem kind of regularly?
Yeah.
Or no, these still work. But these have a very special relationship that'll work every single time if we're missing a leg, for example. It's easier and faster. Okay, so aside from having special right triangles, we also have something called similar right triangles and congruent triangles. So similar triangles have the same angles with proportional sides. Congruent triangles have the exact same sides and the exact same angles. So of course, we're just going to write that out as a nice, friendly little reminder. I'm also going to draw an example just so you can see what I mean when I'm talking about similar triangles. That's fine. Okay, so this right here would be an example of proportional and similar triangles. They're each a 45, 45, 90 degree triangle. The legs on this one are 3 and the hypotenuse is 9. The legs on this one are 1 and the hypotenuse is 3. The side lengths on this one are 1/3 the side lengths on this one. That's what I mean by proportional. So each one of these lengths was divided by 3, thus creating the side lengths on this similar triangle. Okay, that exact same relationship has to exist on all sides of our triangle in order for the relationship to be similar. After similar triangles, we also have congruent triangles. And these congruent triangles have these same angles and the same side measures. So, for example, these two triangles are congruent because they have the exact same measurements in the exact same places. So each of these has a hypotenuse of 15. Each of these has a longer leg of 12. Each of these has a shorter leg of 9. Where the 9 and the 15 meet, they have the same angle. Where the 12 and the 15 meet, they have the same angle. And they each have a right angle where the 12 and the 9 meet. So these are exactly the same. One is just turned to make it look different. Do not be fooled. Okay, congruent means everything about them is the same except maybe for the way it's written or like the direction of it being written. Questions, concerns, or issues with similar or congruent triangles? We're okay. Yes, Jeremiah. Your question. Now you're just stretching? Okay, so now we actually get to get into the fun stuff. I'm going to give you twice as much homework, Stephen. Twice, and just you.
Turns out she gives you like today's homework and tomorrow's homework.
Without even teaching the books. Students are not here.
Now that we have perfected our understanding of right triangles, we can start working with trig ratios associated with these right triangles. So before we can get too far into it, we need to identify what our trigonometric functions are. Some of these may look familiar to you, some of them may not. So the three basic ones are sine, which is written S-I-N, and then we use theta to represent an angle. Cosine, which is C-O-S, and then we use theta to represent an angle.
What's theta?
The circle with the line through it. It's a Greek symbol.
Do I have to learn that if I go into Greek life?
I don't know if they do number
All
systems.
about that.
Okay, and then tangent, which is tan, and then the theta. We could always use it, like an x, which is theta, works better because we use variables other places. So these are the three basic trig functions. There are three more that you maybe did not learn in geometry. So the first one is cosecant.
What?
And that is CSC with a theta.
No, I remember these.
Then we have secant, which is SEC with a theta. And then we have cotangent, which is COT with a theta.
These being talked about, I don't think we ever used.
No, in geometry, you should have just used sine, cosine, and tangent. There are three B's.
I remember cotangent.
Maybe.
I remember.
Good, that's good.
Cotangent's actually.
Yeah, I
So
remember
not from
this.
that section or what thing?
So Kotoa is going to be these three.
So.
See, I don't think
Stop
I saw
it.
these on the
Stop it. Okay, so there is something that we really, really need to note here. This is a question that I love throwing on an exam or a test or both, because it's something that a lot of you will mess up on because it's a really common misconception. When we are taking the trig ratio for an angle, we can only use the acute angles in the triangle. So trig functions only apply to the acute angles in a triangle. And only in a right triangle. This means that 90-degree angle, we can never, ever, ever take the trig value of. Okay? It'll never work.
Am I supposed to have that big calculator?
The graphing calculator,
Yeah.
you're going to definitely want it.
He already lost it.
You don't need it today, but you will need it. Okay, does everybody have that written? If I were you, I would circle this or star this or box it in, because this is the number one question that I see missed on a quiz or a test, and it's a great trick question to throw in somewhere. And I'm talking wonderful trick question to throw in somewhere.
Is it gonna be on homework?
And I will always, always throw it in. Always.
Think so?
No, it's not on homework.
You can't pull
She's like, geometry 7.
Okay, so these trig ratios are very specific to the sides of a right triangle. So what we need to do now is we need to practice identifying specific sides to a right triangle in regards to the angle theta we're working with. So for example, if I am given this right triangle and I am identifying this bottom right angle as my theta angle, we can also go ahead and label our vertices in case that's helpful as well. So right now, angle A is the theta that I'm dealing with. Okay? These trig ratios have us identifying our triangle sides as three things. One is the opposite side, one is the adjacent side, and one is the hypotenuse. Which one of those things do you think we will always be able to identify first? The hypotenuse, because it's the same all the time. Which one of these sides is my hypotenuse?
A to C.
A to C, because it's the diagonal across from my right angle.
Should you write that as like C, A, and then a line over?
Yes.
You can, but I'm not worried about that. That's fine. AC with a line over it, line segment AC, you're good. Okay, so that one is always, always, always going to be the same. The other two, however, will change depending on which angle we identify as theta, or which angle we're looking at. So a good thing for me is I've already identified that this angle right here is the one that I am thinking about and taking this into consideration about. So the other two sides I have to find are the opposite side and the adjacent side. The opposite side is always the side directly across from whichever angle I'm calling theta. So on this one, it's going to be the left side.
So are you trying to
sorry.
find that angle? Is that what you're trying to do?
We'll get there. So if that's the opposite side, then the adjacent side is always the side that's touching the angle that I'm looking at. Okay, so this bottom one, BA, would be my adjacent side. As I noted before, the opposite and the adjacent will change depending on which angle I'm considering for my trig function. So for example, if I have this same triangle, but instead I have made angle C up there my theta, which side is my opposite side now?
AB.
This one on the bottom. Which means that which one is my adjacent side? Because it's the one touching my theta. And what's the last side that I'm missing?
Hypotenuse.
My hypotenuse. If you get tired of writing this out all the time, because I do as well, you can abbreviate them. H can be hypotenuse, O can be opposite, and A can be adjacent. Opposite and adjacent will change depending on which angle I'm considering for my trig function. Please do not forget that. The hypotenuse will never change. So what we're going to do now is we're going to practice identifying opposite, adjacent, and hypotenuse sides on a triangle, depending on which angle we're looking at. And then we'll move into the actual trig function part of it. Okay? So I'm just going to draw a triangle. I'm going to tell you which one's theta, and you're going to label the sides on your own. So let's say that I have, I don't know, some nice, pretty, beautiful triangle.
Like a rooftop.
It is kind of like a rooftop.
Might as well just draw the house underneath. Make it a little bit easier for us.
And that's not us, it's okay. I'm gonna say that angle C is gonna be my theta here. I would like for you to identify on your own the opposite side, the adjacent side, and the hypotenuse side of this triangle. You can just do O, A, and H, because that's easier than writing all of those out every single time. What's your question?
If the triangle doesn't have A, B, or C, it doesn't matter which.
If it doesn't, if it has like X, Y, or Z, or
No, I give it doesn't have any.
there will still be something telling you which angle we're considering. Are you looking at the homework right now?
No.
Okay,
I mean, it's up and I wasn't looking at it. I just remember it back.
right. So I'll show you what determines what it is. Okay.
There was, I think there was something that told us how to write what angles we wanted.
I'll show you. Boone, tell me one of the sides. AB is opposite. How did you know that?
Since it's across from the theta.
It's across from the theta. Perfect. Zach, give me another side.
BC is
Adjacent. Good. How did you know that?
it's on the same side as
Theta. As the angle. You can just say angle. That's fine. And then which one's my hypotenuse, Jeremiah?
AC,
Perfect. How did you know that?
because it's across from 90 degrees.
Because it's across from the 90-degree angle. Do we need to do more of these?
no.
Or are you okay?
Okay.
Is anybody confused about opposite, adjacent, and hypotenuse sides and identifying them based on the given angle? We're good. Okay. So now we will understand why that's important. So let's say that we have a generic triangle right here. Okay? On this triangle, I have A and C, and we're going to say that theta is this bottom right. Of course, that means that BC is my opposite side, BA is my adjacent side, and CA is my hypotenuse, right? That was pretty easy for me to figure out. This is important because each of my trig ratios can be written in terms of an opposite, adjacent, and hypotenuse side of my triangle. So our most common trig function is going to be sine. So if I'm taking the sine of angle theta, this means that this will be equal to the opposite divided by the hypotenuse. So whatever the measure is of that opposite side is going to go on top, and whatever the measure is of my hypotenuse is going to go on the bottom. So each of these trig functions in regards to an angle is equal to a fraction. So sine is equal to opposite over hypotenuse. Cosine then, our second most popular trig function, is equal to my adjacent side over my hypotenuse.
Isn't that what's proposed here?
Yes, we'll get there in a second. Tangent then is equal to my opposite side over my adjacent side. So everywhere you see an opposite or an adjacent or a hypotenuse, we're just plugging in the length of that side. Of course, each of these three has a corresponding secondary trig function. So sine's corresponding secondary trig function is cosecant. So cosecant of my angle is equal to hypotenuse over opposite. Cosine's corresponding trig function is secant, and that is equal to hypotenuse over adjacent. And cotangent corresponds to tangent, and it is equal to adjacent over opposite. This is where our nice little SOHCAHTOA that you may have heard of comes in. So I'll give you guys a second and then I'll show you what I mean. If you don't like SOHCAHTOA, you can come up with something else. Actually, you have an assignment where you do come up with something else, just for fun.
I can just come up.
I'm going to show you in a second. Okay.
Come up with a random.
Okay, so this is SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So the order that it's written in actually tells you which sides correlate to which trig function. So sine
So can you make like an acronym?
is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent, which is how they came up with SOHCAHTOA. See, isn't that kind of cool? If you can't remember, you can be like, okay, so O over H, opposite over hypotenuse. So something that you guys will do, not today, is you will come up with your own saying or acronym or anything that will help you remember all 6 of these trig functions. We're not going to do it today. I know when I did it in high school for the H over O, I don't know, I said somebody was a hoe. Because H over O is hoe. It's the only way I remember that. Please don't do that. That was very derogatory, and I know that now. But it's just whatever makes you remember it. And then I let the class vote, and the person with the most voted on acronym or saying gets extra credit. So it is helpful.
Everyone in the vote for itself.
But then I also get to vote.
Oh, frick.
Yeah, so then you're the tiebreaker.
Exactly. Okay. So SOHCAHTOA should be somewhere on your paper so you don't forget if that is helpful to you. I think it's helpful because it's really easy to remember the first 3. So now what we're going to do is we're actually going to practice using these relationships to find trig values for specific angles. Okay? So I'm actually going to put numbers with it now.
Whoa.
Let's say for our first example that we have this wonderful, beautiful right triangle. Where angle B is my right angle. Angle A is across from side 4, or side measure 4, and then angle C is across from side measure 3. Can everybody see that?
Yes.
Okay. And we're just gonna practice finding all the trig functions related to one of these angles. Am I ever gonna use angle B here? Why not?
It's a right angle.
Because it's a right angle, it's 90 degrees, it's not acute, these don't apply. So I'm either using angle A or angle C. We're actually gonna do a set for both, just to practice, okay? So the first thing I would like to do is I would like to find sine of angle A. So I write that as SIN, because that's the abbreviation for sine, and then the angle that I'm looking at. So here, that's A. So I need to look back at my list of trig ratios, and I need to identify that sine is what over what? Opposite over hypotenuse. So what side is opposite angle A?
4.
What's the length of my hypotenuse?
5.
So sine of angle A is equal to 4 over 5, and that's it.
You don't have to do any math.
Only thing you'd have to do is reduce the fraction if possible. So then let's do cosine of angle A. Cosine is what over what?
Adjacent over hypotenuse.
Adjacent over hypotenuse. Steven, what's my adjacent side to angle A?
Will that be AB?
Which is length what? Yep. And then Landon, what's my hypotenuse length?
5.
So cosine of angle A is simply equal to 3 over 5. I'm gonna let you do tangent on your own. Again, in regards to angle A. Cassie, what'd you come up with? 4 over 3. So tangent is what over what originally? Opposite over adjacent. So I do agree because my opposite side is 4 and my adjacent side is 3. Who got that right? Is anybody confused by any of this right here? Are we okay for the most part? I want to go ahead and switch up which angle we're using now, which is why I didn't put a theta on the triangle, but we can use those corner vertice letters just the same. So now I would like to find sine of angle C. Sine of angle C here. Jonah, what'd you come up with?
It would be
3 over 5, because the side opposite C is 3 and the hypotenuse is 5. What would be then cosecant of angle C?
Okay, I didn't do that.
So do it now.
How do you get down the calc?
You don't. That's why we're not using the calc. I'm looking only at those. We will eventually get on the calc, but we're not right now because we don't need it. Kennedy, what is cosecant of angle C?
5 over 3.
5 over 3. How'd you get that?
Because it's the hypotenuse, which is 5, and the opposite, which is
Perfect. It is also the opposite of sine. So I know my sine was 3 over 5, so cosecant must be 5 over 3. There's a reason that I wrote them across from each other up here. If you notice, cosecant is just sine flipped. Secant is cosine flipped, and cotangent is tangent flipped. They are opposites of each other. Eventually, you will have to memorize that, not today. But that is helpful information to know. That's why I color-coded them and wrote them across from each other.
That's great.
Right?
Hiding secrets all
Of course. Okay, so now I would like for you to find, cotangent of angle C. Oh, I should probably bring that down, sorry. Chandler, what'd you come up with?
I got 4. Yeah, 4 thirds.
4/3, because it's gonna be adjacent over opposite. Who else got 4/3? Perfect. One last one. I think we're ready to move on to the next problem.
We're ready.
You ready? I want tangent of angle B.
No,
Why not?
Sorry.
because that's a right angle.
Because it's a right triangle, not a right triangle, a right angle in my triangle.
So what do you write?
You just say
No.
No.
not possible, or undefined, or can't do, or I refuse. That would be okay
Can I
too.
put no?
Sorry.
Just
but
no.
according to the math- No, no, you're fired.
No.
Wait, what does your calculator say when you type in something?
Probably says.
It'll probably like say a syntax error or something like that.
Yeah. we're gonna put that.
Okay,
Syntax error.
so I'm actually gonna pause here because I want you guys to have a chance to look at the homework and ask questions about that. You are only doing, I believe it's 1 through 18. Okay, so you're not gonna do those last ones that look really confusing. It's really just this on your homework,
It's super duper.
okay? Is anybody confused by any of this that we have done? Are we okay?
Yeah.
Okay, get your homework out and start working.
So how do we do number one?
Is that all we're doing?